Let's learn how to integrate rational functions by using the partial fraction decomposition. For example, here is a rational function. The numerator and the denominator are some polynomials of x. On the right, there is a partial fraction decomposition. So instead of one fraction, we have made two fractions, and it seems that this denominator will be 0 if and only if x is 0, and this denominator seems to be equal to 0 if and only if x is equal to minus 1. So each of these denominators have just one 0. So how will this help us? If we need to study an integral like this, we don't know what is the integral function of this function. But if we make the partial fraction decomposition, then we know how to integrate these functions. The integral function of 1 over x is just natural logarithm, and the integral function of this is natural logarithm of x plus 1. And then we just need to substitute the values of x, and from the upper limit we get this, and in the lower limit we get this, and it seems that this and this are with the plus sign, and by using these formulas we can combine everything and we obtain our answer. Next question is, how about when we have that the numerator and denominator are just some polynomials? Let's recall how we can divide polynomials. If we would want to calculate this limit, we could use, for example, the L'Hopital theorem, and we would get the derivative of the numerator is 2x and the derivative of the denominator is 1, and we would just get 4. This is the new method what was introduced in this course, actually in the autumn already. The more simple way to solve this would be to use the quadratic difference formula. So a difference of two squares is the product of the difference of the numbers and the sum of the numbers. So we would get something like this, and we can cancel out these terms, and we will just get 2 plus 2. That is 4. The same answer. And the thing of course worked because 4 is equal to 2 to the power squared. If we would want to calculate this limit, it wouldn't be so easy. We wouldn't know how to get a factor of x minus 2 in the upstairs, so we could cancel it out. However, in the autumn we learned a method how to calculate this fraction. So we want to divide this polynomial with this polynomial. How many times does x go to x cubed? Well, it goes there x squared times. Then we will take x squared and multiply it with x. It gives x to the power 3. And in the same way, x squared times minus 2 gives minus 2x squared. Then we change the signs and we calculate this addition. x cubed will disappear, minus 2x squared will also disappear, and we can drop this one down here. We will get this factor like this. And now next, how many times x goes to this? Well, it goes there 3 times. And now we multiply 3 times x is 3x. And 3 times minus 2 is minus 6. And then we change the signs and we calculate. We will get 0. So 0 is the remainder. So this is what we got. And it seems we can calculate the limit now. We will just set x to be 2 and we will get 2 squared plus 3. This gives 7. So if we have this kind of integral and we have that the degree of a is at least the degree of b, then we can make a division. We will get the quotient and the remainder, and for the remainder we will have that the degree of the remainder will be strictly less than the degree of b. For example, in this example, the degree of the denominator was 1 and the degree of the numerator was 3. After division we got the quotient whose degree was 2, and then we got the remainder there, and clearly its degree is maybe it is 0 or maybe it is even less. So this will work. So for example, for this fraction it happens so nicely that the fraction is a polynomial and it's super easy to integrate. So we can handle this polynomial. But how about this quotient here? So the next question is how we can integrate these kind of fractions of two polynomials where the polynomial in the numerator has a degree less than the polynomial in the denominator. And the numerator is not identically 0. The next thing is that we need to find the zeros of b and write the factorization of b. Well, b will be some polynomial, so it will have a factorization. Maybe there is some constant, and then there can be some terms such as these kind of first degree terms. Then it can happen that there is some factor which is to a power larger than 1. So we can have some factor where the power is 2. And it can happen that there is also some factor there which is always positive. We would know how to decompose this kind of polynomial by using the complex numbers, but we don't have to do this. Next, we can write our quotient in this way. We can pick up these factors from here and make terms which correspond to these. We can have a factor which is related to the first term. We can have a factor which is related to the second term. The third term is a little bit different because it had the power 2 there, so we can have some kind of factor like this. And how about third term? Well, we will have a factor for that also. Yeah, and what to say? These factors here, they are the most easy case, then this would be the second easy case, and this maybe is the most difficult one. Of course, for some polynomial b, not all of these factors happen, so it can be that we just have these first two factors and these are not existing there, so our composition will be looking much more easy. So let's consider different cases where we have different factors. Let's study this integral. So our function r is now 1 and our function b is now this. And we are supposed to find the zeros of b. Well, b is 0 if and only if x is like this and divided by 2, so we will get that x has to be, okay, x has to be minus 2 or 1. Because of this 0 we will get this factor, and because of this 0 we will get this factor. So we have done step 2. And step 3 would be to write we will write a formula like this, and then we need to solve for these constants. Let's multiply with b. In the left hand side we will have just 1, and in the right hand side we will have this times this. The x minus 1 will cancel out and we will just get a times x plus 2. On the other hand, this times this will give us b times x minus 1. In the right hand side we have x a times and b times, so we can write this, and we have number 1 to a times and minus b times. We get a linear group of equations and we can solve this in MATLAB, for example. This is what we will get. A is equal to 1/3 and b is equal to minus 1/3. If we want to calculate by hand, there is even a more easy way to do this. The equation should be true for all values of x. So we can, for example, set x to be equal to 1. In the left hand side we have 1, and in the right hand side we will have 3a plus b times 0. And from here we can easily get a is 1/3. On the other hand, if we set x to be equal to minus 2, we will get that 1 is a times 0 plus b times minus 3. And this gives easily b equal to minus 1/3. So we can use a group of linear equations, or we can use this calculating by hand method. It is sometimes called the Heaviside method. Then we are ready to integrate. This is our integral. We were able to integrate, And because here is 1/3 and here 1/3, we can actually combine these logarithms. But this is not so necessary. How about if we had a factor like this? What would happen? Let's consider this integral. Now we are already given the factorization of b. Let's look for the partial fraction composition. Because of this term here, we will get this term. And because of this second degree term, we will get this term. Multiplying with b, we get this. By setting x equal to 2, we get this. By setting x equal to 1, we get this. By setting x equal to 0, we get this equation from where we get that c must be 5. And substituting it to this equation, we get that 2b is equal to -4. That means that b is equal to -2. So we found the values of our constants. Now our partial fraction decomposition is ready. It seems that we can write this numerator in a little bit different form. 2 times x minus 2 plus 1. Sorry, minus 1. So our integral seems to be equal to the integral of this function. Let's call this function, for example, f. And I think we can write what the integral is. We will get a minus logarithm of x minus 1, then minus 2 times the logarithm of x minus 2, and then we need to have this term and this term. We were able to do it. If we are given this integral, the answer is easy. We will just get the arctan of x plus a constant. Let's see about this integral. Our b is here, and b will be equal to 0 if and only if x is equal to something like this. Now in the root we got here -7, so there are no real roots. So we really have this kind of situation where we have a second degree polynomial with no real roots. Let's complete the square. If we would have some factor like this, we would get like this. If we would have a plus, we would get plus. So let's try. Our function looks like this, and we want to have it in the same form with the number 2 there. So let's force a number 2, and then we have the x, and now to make these terms equal, what is our a? Our a needs to be -1/2. Then we need to have a plus a squared. So let's add it there. Plus 1/2 -1/2 squared. And let's now subtract it again. Well, we need to subtract 1/4, and then we are missing our number 2. Now we are ready. We can use our formula for this factor here. And what we will get? We will get x minus x plus -1/2 to squared plus, and these things here will give us 2 is a divided by 4, so we'll get in total 7/4. 4. We are done. We want to use this formula, so let's denote this thing here by t. This term here is troubling us, so let's do like that, let's multiply the numerator and the denominator with 4 by 7. This is what we have. Then we have done the integration. We can remember what t is. And our answer is ready. So in conclusion, if we have a fraction of two polynomials, we can make a division so that we'll get a polynomial plus a fraction where the numerator has a smaller degree. Then for the denominator we can find the zeros and the factorization, and based on that we can write the partial fraction composition and need to find the constants there. What are the constants? And after doing this we can integrate.